Hey everybody, welcome to our first video on Unit 12, which is all about the 4 different types of solids. Before we get into the different types of solids, however, let's just refresh our memory on the energy that the different types of solids have, those particles have in those types of solids. So here is sodium metal in all 3 states of matter. So I have sodium metal, which you might remember is actually soft enough to be cut with a knife. It doesn't really look like a metal here, but in real life, this would be pretty shiny, and it's a great conductor of heat and electricity. So here is sodium metal, or solid sodium, and these particles will vibrate back and forth. So they're kind of being shown there in this image. They kind of look a little bit blurry. And that blur is a result of those particles vibrating back and forth. Particles are always going to be in motion in some way. And unless you're at absolute zero, which is 0 Kelvin, or negative 273 degrees Celsius, all particles are always moving. So even when something is totally solid, like this pen, all of these particles in this pen, despite them being a solid, are still vibrating back and forth. In order to go from a solid to a liquid, we have to increase the temperature. And that increase in temperature is adding more energy to those particles. So not only are these vibrating back and forth, but the particles also have translational energy. And this translational energy means that the particles can slide past one another. So not only are they moving like this, vibrating, but they also could slide past and move between one another, which is why solids are able to take the shape of the container that they're in. So this solid sodium metal retains its shape because they're not sliding past each other. Here, those particles can move past each other because of that added translational energy. If I increase the temperature even more, we not only have vibrational and translational energy, but we also have rotational energy. So they're vibrating, they're sliding past one another, but these are also rotating. So I'm just going to draw rotating like that. And because they have all 3 of those types of energies, they're really far apart from one another. I mean, we already talked about the kinetic molecular theory of gases. Particles are far apart relative to their size. So they're really, really, really far apart. They're also not attracted nor repelled to one another. You can look back at the kinetic molecular theory of gases if you so wish. But we are going to use this information when we talk about the different types of solids. And there are 3 types of bonds that we've talked about in that Chem 1 review. There's covalent bonds, there's ionic bonds, and there's metallic bonds. And those bonds make up the 4 types of solids. Now, you see I use the word solids in quotes there, and that's because you're going to find that these are not always all solids all the time. We say solids, but some of these substances are liquids at room temperature, and there also could be gases at room temperature. So even though you might hear me say solids, they're not always going to be a solid. And these solids, again, can be described in terms of the types of elements that make them up, but also the types of intermolecular forces that exist between those particles in those solids. We're just going to focus on the types of solids first, not on intermolecular forces. That's going to be in another video that comes after this. So those 3 types of bonds make these 4 types of solids. And these 4 types of solids are ionic, they are covalent network, metallic, and molecular. So those first 3, of course, ionic and metallic, are going to be formed from the types of bonds, ionic and metallic, whereas covalent network and molecular are made up of covalent bonds, but there's something else that makes them quite different, which is those intermolecular forces, which we'll get into later. Let's just talk about the 4 types of solids first. So your first type of solid is an ionic solid. And ionic solids are very orderly arrangements of charged particles that are held together by electrostatic attractions. And if you're not familiar with the phrase electrostatic attractions, these just mean that positives and negatives attract one another like a magnet. So positives and negatives attract. In chemistry, that's what we call an electrostatic attraction. Because we have these positively and negatively charged particles, like a magnet, they attract one another. And when they attract one another, they're going to arrange themselves in a very specific way, so that way they minimize their potential energy. They want to try to form these very orderly arrangements. Each anion wants to be surrounded by as many positive ions as possible. And the same goes for positive ions. They want to be surrounded by as many negatively charged ions as possible. And that's to minimize their repulsive forces, because positives like negatives, they want to be surrounded, and negatives like positives. So when they do that, they form these really nice crystal lattice structures. Now, normally there's not going to be all the space in between the particles, but they're trying to show that arrangement of those within this 3D structure here. So how do ionic solids form? You might remember that ionic bonds form between a metal and a non-metal, and there is a very specific reason for that. So you have a metal, in this case sodium, an alkali metal, group 1, has 1 valence electron. Very low electronegativity, wants to get rid of that 1 valence electron very easily. It's going to bond to a non-metal, in this case is chlorine. Chlorine has 7 valence electrons, has a very high electronegativity, wants to steal an electron from something, steal or share. In this case, that non-metal is going to rip that electron away from sodium. And to do that, so here's a nice little animation that I made. So chlorine is going to rip that 1 electron from sodium. And when it does that, they both satisfy the octet rule, right? We've talked about this back in Chem 1. When sodium loses a negative thing, it becomes positive. So when you say, you know what, I'm going to forget all of the bad things that happened to me, I'm going to become happy, right? You're forgetting about the negative things. So if sodium is losing a negative thing, it itself becomes positive. And if chlorine is gaining a negatively charged electron, it becomes negative. That fact that I have positives and negatives as a result of that ionic bond, that's where we form an ionic solid. The fact that positives and negatives attract one another like a magnet. And we call that a formula unit. So because 1 sodium atom exchanges an electron with 1 chlorine atom, it's a 1-to-1 ratio. We call that 1 formula unit. And a formula unit is just a lowest whole number ratio of ions represented in an ionic compound. So because we have 1 sodium exchanging electrons with 1 chlorine, we call that 1 formula unit. If you have calcium and chlorine, for example, calcium has 2 valence electrons and chlorine has 7, they will exchange electrons in a 1-to-2 ratio, so CaCl2. That would be calcium chloride's formula unit. And you could always figure that out just by writing the formula for something. So what are the properties of ionic solids? Based on their structure, what properties do ionic solids have? So down here towards the bottom, we could see what I meant before, that there really is no space in between those particles. But ionic solids, what happens? These are crystalline in nature. So salt, for example, salt is a highly crystalline structure. Every single one has the same exact shape. They're all little squares. So here's salt blown up, that we could see those crystals. They have a very specific shape. If I look at this, this is a cube, right? Here's a cube. They are crystalline in structure. Something else, they are very hard and brittle. So they're going to be hard to the touch, but you can break these very easily. This is known as cleaving along a surface. I can take an ionic solid and hammer it, and it'll break right there. I could take something else here. Look at these straight lines within this structure. Here's a straight line. I could take it and break it right along that line right there. They're very hard, but they can be broken very easily because of this very orderly arrangement of particles. They're also soluble in water because they're made up of charged particles. These dissolve in water. That's what soluble means. We're going to show that in an animation on the next slide. These also conduct electricity when they dissolve because they have these charged particles, which allows for a flow of electricity. And they conduct electricity in the liquid state, again, because those ions are freely moving. They do not conduct electricity in the solid state. So if you were to take a conductivity meter to a solid piece of salt, so this looks like the conductivity meter we used in that mind's eye lab on the first day of school, this would not conduct electricity. Not conduct. And that's because you don't have any freely moving ions or freely moving electrons there. What I want to talk about is this in particular, the soluble in water, and we'll say conducting electricity when it's dissolved. So why does this happen? Why do ionic solids dissolve, and why do they conduct electricity when they're dissolved? So here is just a hunk of salt. You'll see you have your sodium ions and your chloride ions in a very nice orderly arrangement. So notice how this chloride ion is totally surrounded by sodium ions, and this sodium ion is totally surrounded by chloride ions. And then I introduce water to this crystal. So here are some water molecules. And of course, they're vibrating and they're translating. We're not going to show translation here, but they are in fact moving. Water, we know, is a polar molecule. So it has positive and negative sides to it. Because it has positive and negative sides, it is attracted to the positive and negative ions in the ionic crystal in salt. So what happens is these water molecules start to arrange themselves so that way they can pull those ions off of that crystal. So look, right here, this is oxygen. This dot right here, or these circles, are oxygen molecules. And those little tan ones are hydrogens. You can't really see the oxygens there, but you get the idea. Because this is polar, this oxygen has a partially negative side to it. So this right here is also partially negative, this oxygen. This is partially negative, and that's partially negative. Because water is polar, it can pull those cations off of the crystal, which allows the crystal to dissolve. So that's what it's showing here, this partially negative side of water, that oxygen atom, is pulling those sodium ions off of the crystal. What about the chloride ions? Well, chloride is an anion, so the water molecules will arrange themselves like this in order to pull those chlorides off of the crystal. They're going to arrange themselves in a way so that the partially positive sides of hydrogen, so here's a hydrogen, here's a hydrogen, these are partially positive, they are going to surround this anion, this negatively charged chloride ion. And this will happen until either A, you ran out of salt, or B, you've reached its saturation point. So that means there's not enough water molecules available to completely dissolve the salt. So this animation is just going to keep going, right? Notice that the partially negative sides of oxygen always surround themselves around the positively charged sodium ions. So that's what this was showing here. Notice how it's always going to arrange itself like that. Because now I have these ions that are dissolved in water, electricity is able to flow through this very nicely. The electrons can move throughout that, and these conduct electricity really, really well. Because when salt or when any ionic compound melts and you have that added translational energy, the ions can slide past each other, which also allows for electricity to flow through them. But like I said, you're not going to see that when you have just a hunk of salt crystal in front of you, Because those ions can't move, there's no electricity that's conducted. So let's talk about covalent network solids. So of course, covalent network solids are going to have covalent bonds in them. But a key to this is that word network. So a covalent network solid is a chemical compound in which the atoms are bonded by a continuous network of covalent bonds that extend throughout the entire material. So a great example, or two great examples of covalent network solids, this right here is actually graphite. So this is carbon, which is a solid, but this is known as graphite. And we'll see here that this graphite actually forms in sheets. So I couldn't really find a better picture for this, but I have 3 sheets that are here. And these form covalent bonds in these very flat sheets like this, which is why you're able to write with a pencil. It's actually leaving behind little carbon sheets. But an even better example of a covalent network solid is a diamond. So this is also solid carbon, but this is a diamond form. And diamonds are literally one giant molecule. And that's because if this is a carbon atom and this is a carbon atom, you have covalent bonds in between every single carbon atom in that structure. So diamonds, this diamond right here, literally a giant molecule of carbon, because every single carbon atom is bonded to the next via a covalent bond. And that's why covalent network solids have the properties that they have. If my husband bought this very expensive ring and I were to wash my hands and the diamond were to dissolve, he would be very upset. So covalent network solids have very high boiling points and melting points, and that's because it is very hard to break these covalent bonds that are in between every single atom in the structure. This right here is actually silicon dioxide, which is quartz. And if you go to the beach, every grain of sand is a quartz molecule. So literally, you're walking on individual molecules on the beach, because every single silicon atom is covalently bonded to oxygen atoms in this structure. So this is like one giant grain of sand that you would walk on. They're one big molecule. They have a network of covalent bonds. Here's a bond after a bond after a bond after a bond in every which direction. These also are very, very hard. So if you think about geology and the Mohs hardness scale, which you might have learned about in another science course, what could scratch another diamond? Only another diamond. They're very, very hard. And again, it's because those covalent bonds are super strong when they act as a network. It's very hard to break them. And again, these are also insoluble in water. They do not dissolve. There are no positive and negative charges, so they are unable to pull these particles apart from one another. The next type of solid is a metallic solid. And of course, these are going to be what hold your metals together, or just metallic bonds in general. Metallic solids are composed of positively charged metal atoms with overlapping electron clouds that allow for electrons to be delocalized. And delocalized just means that they don't belong to one atom. They belong to the whole entire system, the whole entire structure. So surrounding all of these positively charged metal ions, we can just say this is iron, for example. So every single one of these is an iron ion. Surrounding this, we have one giant electron cloud. So just imagine that there's an electron cloud. I can't really draw it on my pad, but just imagine that this whole entire thing is in one massive cloud. There, I was able to draw the cloud. So this is all one electron cloud. This red thing. This is an electron cloud. And within that cloud, the electrons are constantly moving. So I have an animation here. These electrons are always flowing throughout this one giant electron cloud. And because of that, that allows for metals to have very specific properties that are different from ionic and that are different from covalent network. And it has to do with the fact that these delocalized electrons are constantly flowing throughout this material. So metallic solids are very good conductors of heat and electricity, and that's because those electrons are constantly moving. That's what electricity is it's a flow of electrons. So because metallic solids already have that flow of electrons, you can conduct electricity really, really well. These are also malleable. Because those electrons are moving, you can take a hammer and you can make this become flat like a pancake because the electrons are flowing with it. These atoms could slide past each other and they could form a different shape, and the electrons move with it. That also allows for them to be ductile. So ductile means you can pull it into a wire. So this right here, malleable, of course, means that you can hammer it down flat, whereas ductile means you could pull it into a wire. They're also very lustrous, and lustrous means shiny. This has to do with the fact that light can reflect off of the surface because those electrons are constantly moving. And it's hard to determine their melting points and boiling points because metals vary. Of course, mercury is a liquid at room temperature. Gallium has a melting point that allows it to melt in your hands, whereas tungsten has one of the highest melting points of all of the metals. So it's kind of hard to predict whether a metal will be a solid or a liquid at room temperature. So lastly, let's talk about molecular solids. So this is the one where we're not going to see that they're solids very often. So I'm especially going to put solids in quotes here because a lot of times your molecular solids will not, in fact, be solids. And molecular solids are small molecules that are held together by your intermolecular forces of attraction, which we didn't talk about yet. We're going to talk about intermolecular forces in the next video. But many times they're going to be small molecules. So one example would be water. Water would be a molecular solid, which, as we know, is not a solid in itself at STP. It's a liquid. And another example would be carbon dioxide, which of course we know as a gas at room temperature or at STP. So sometimes you'll see molecular compounds in fact being solids, but sometimes they're not. And this is, like I said, it's going to tie into a lot with intermolecular forces in the next section. So let's talk about how molecular solids form. We talked about ionic solids being formed as a result of that transfer of electrons, whereas molecular solids are formed when their electron clouds overlap. So let's just say this is two hydrogen atoms. So here I have one hydrogen and it's one electron in a 1s electron cloud. And here's another electron for hydrogen in its 1s electron cloud. Atoms want to bond to one another because they're more stable when they're bonded to one another. So these two electron clouds get close enough to one another that they will overlap. And this overlap right here is the sharing. So this right here is the sharing of those two electrons. Sharing of two electrons. So that way they both have that full first outer shell. The 1s sublevel or the first energy level period can have only two electrons. So once it has those two, it becomes a stable molecule, hence why helium is stable in its elemental form. So molecular solids form when electron clouds overlap. This overlap allows in the sharing of electrons that are associated with covalent bonds. This is also true for covalent network solids. Those atoms become close enough to one another that their electron clouds overlap, but in that case, you have an overlap of electron clouds throughout the entire structure. Here, we have very small molecules, and those small molecules are not bonded to one another. So like two water molecules aren't bonded, but they're attracted via an intermolecular force, which we'll get into later. So what are some of the properties of molecular solids? Molecular solids are going to have low melting points and boiling points, and we consider low to be less than 300 degrees Celsius. So for example, here's iodine. Iodine is made up of all nonmetals, and it has a very low melting point. In fact, its melting point is 114 degrees Celsius. We can melt that on a Bunsen burner in class. Peroxide is already a liquid at room temperature. It's already melted, so very low boiling point. And aspirin, again, all of these are made up of nonmetals, and that's one of the keys to molecular solids, is that they're made up of all nonmetals. Nonpolar molecules do not dissolve in water, nor do they conduct electricity, and that's because there's no charges. So because water is very polar, if you have a nonpolar molecule, they don't like one another. And that's because water has charges, but the nonpolar molecules don't, so they're not able to attract one another nearly as readily. However, if you do have polar molecules, they will dissolve in water because they too have positive and negative sides, which again, we'll get into when we talk about intermolecular forces. So let's just take a look at this image right here. And this is just a really nice overview of those different types of solids and some examples and some of their melting points and boiling points. Some of the easiest ones to recognize are ionic and metallic. Of course, metallic, these are just going to be metals, whereas ionic is always a metal bonded to a nonmetal. So if I look at these examples here in the formulas, I have a metal bonded to a nonmetal, metal bonded to a nonmetal. Boiling points and melting points are very, very high. So they are well above 300 degrees Celsius. That is very normal for an ionic solid. Metals as well. So all of these are just metals, but notice how their melting points and boiling points vary quite a bit. That's common for metallic solids. The best way to tell if something is a metal just by a description is the fact that it's lustrous or shiny, or that it conducts as a solid. Conducts as a solid, or any state of matter, really. Those are your best tells as to whether or not something is metallic, is that it's very lustrous and that it conducts as a solid. It's the only material that can conduct as a solid. Covalent network, these have even higher melting points and boiling points. However, this is a very small class of compounds right here. So I'm going to say very small class. Unfortunately, I'll just have to memorize the species that are covalent network in nature. Your biggest ones would be diamond or graphite. So I'll put graphite here as one. And you also have silicon dioxide. You will always have a covalent network solid for diamonds, graphite, which both have C as its general formula. This X just means, depending on how big the diamond is, how many carbons are bonded to it. And silicon dioxide, which again, this just means how big that grain of sand is. Another covalent network solid you might see is silicon carbide, SiC. Notice how your molecular solids here, these have very, very, very low melting points and boiling points. So look, these are all in the negatives right here. And these are very, very small molecules comprised of all nonmetals. So I'm going to write here all nonmetals. Let's get this here. These are all nonmetals. So that's another tell for these. Molecular solids are always made up of nonmetals. Ionic solids, metal and a nonmetal. Metals are always, or metallic, are always going to be your metals. We're going to differentiate between these melting points and boiling points between polar and nonpolar in the next video. But for now, that's the conclusion of the 4 different types of solids. We're going to get a lot of practice with this in class. Hopefully we'll get a lab in there that gets you to experience these different types of properties for them. As always, if you have any questions, let me know. Make a note in your notes. Stop by and see me. Send me an email. Otherwise, I will see you in the next video, which is all about intermolecular forces. So I will see you then. Bye.